We are going to talk about three concepts which are often confused with each other: the concept of parallel computing, the concept of concurrent programming, and distributed computing. Now, often in literature or otherwise also, these concepts are used sometimes synonymously, which is kind of erroneous because they actually mean different things. So let us try and understand what do they actually mean with a small situation, and let us see how these things work. So let me talk about each one of them. We will start with parallel computing and understand what they mean. So parallel computing it uses multiple cores, CPU cores. So the idea of a machine in case of parallel computing is there is one machine which has multiple GPUs, and each GPU may have multiple cores, but let's as a core. So there is core 1, there is core 2, and there is core 3. Core 3, these are basically CPUs. So a given task is broken into smaller tasks, and each core does one of these tasks, and the way these cores communicate is typically through shared memory if they need to communicate. So you have some part running here, some part running here, and all on the same machine. Technically it is one computer with multiple cores which are running together. So that is what is called parallel programming and parallel computing, and it is pretty powerful. We see GPUs doing it all the time. We have the entire story of NVIDIA centers around GPU, and these are used now for all generative AI applications, for all artificial intelligence, for computational fluid dynamics, all of these. But the aspect to understand is that the problem is split into multiple parts and solved in parallel. So just to give you an analogy, if it is an image, let us imagine there is some kind of an image, and we want to make that image, let us say this is some kind of an image with lots of pixels. So each pixel, let us say, has to be converted from its color value to a grayscale value. So what you would do, you would take this bunch of pixels and give it to one core, and they would be converting that part of the image into, let us say, a grayscale image. Meanwhile, this part of the image could be handled by the second core, a third part of the image could be handled by the third core. So basically this is how we would go about doing it, and there would be multiple cores doing this simultaneously, and if they have to share results with each other, that would happen through a common memory space which is called shared data. The use cases for this are generative AI, scientific computation. For example, if you are doing a large bioinformatics application like protein folding or something, you would use this kind of architecture, or complex calculations. For example, you are working in the area of computational fluid dynamics, you would need this thing to solve some of those equations. As I just explained, for doing image processing you would need these kind of things to happen. So the shared memory, multiple cores, the same task is done split between multiple cores, and that is how it does. Typically you need to know some amount of CUDA programming in order to use the NVIDIA GPUs, and we will be doing some of that in this program, a little bit of CUDA programming, but some of you must have done a course on parallel computing too. So let us move on and see how it all happens, and in parallel computing. And so let us look at the second style, which is called concurrent programming, and let us see how is concurrent programming different from parallel computing. In parallel computing, what did we see? There were multiple cores, and one core was processing one part of the image, the other core was processing another part of the image, the third core was processing the third part of the image. In concurrent programming, that is not what we do. Typically there would be a single typically there would be a single CPU and or a limited number of CPUs. So the architecture would be something like this. There would be a given CPU and there would be multiple processes, process P1, process P2, process P3, and there would be a scheduler which is typically part of the OS. So there would be a scheduler. Now what would the scheduler be doing? It would use the given CPU and it would do part of the task on part of P1 on the CPU, and then what it would do is it would do what is called as a context switch. So a salient aspect of concurrent programming is context switching. So what would happen is the process P1 would execute for certain period of time, and after that the scheduler would kind of ask P1 to hold back and do what is called as a context switch, and then the process P2 would start. It would be given a certain amount of time to execute, and then again there would be a context switch and perhaps P3 would start or P1 would resume. So this is how concurrent programming would work. So there would be multiple processes which are acting, so that is common with parallel programming, but each process necessarily will not have a different CPU. There might be a single CPU, and using a scheduler you would make that CPU appear to multiple processors, and so that each is given some kind of a slot to do their work, and then the scheduler's role would be to take away that slot and give it to someone else. So it often involves multiple tasks sharing resources like memory or data, and in concurrent task is more about dealing with lot of tasks at once. So that is how they would do. But if you see, there is no scheduler in parallel computing. In GPU programming or when you are using a multi-core thing, there is no need for a scheduler. Each part of the image was processed by one one core, and there was no need for a scheduler to switch between them. No, that particular core would only deal with that particular part of the image. Here it is not like that. The CPUs are limited, the CPU cores are limited, and it is the job of the scheduler to get the work done from these CPUs through a time shared manner, and that is what a scheduler would do. So lot of web interfaces and all of that would work with this kind of architecture, and obviously this was the architecture used in operating systems like Linux, Unix and all of that, and this is a very contemporary and popular architecture which runs. So that is essentially the difference between parallel computing and concurrent programming. So having seen that, let's look at the third style of programming and see how that works. So let's look at how distributed computing works. So in distributed computing you would have a bunch of machines. These are different machines. Let's call this M1, let's call this M2, let's call this M3. They are different machines, and machine M1 would be doing, machine M1 would have its own memory, own hard disk, own data. So data would be here, and perhaps the same program, like this is what you see happening in Hadoop clusters or any of the big data clusters. The data is split across multiple machines. So data 2, data 3 and so on and so forth. So there would be things happening on multiple machines. So there would be some kind of a central coordinator which would distribute the work to be done on multiple machines. Program P1 would run on this machine, program P2 would run on another machine, P3 would run on them. There would be some kind of a network between them. Most of the time they would be working with their data individually. So it is the job of the central guy to not only distribute the processes so that they run on different machines, and on each machine there would be their own data. So for their data they do not have to go to a central place, so they are fast. So data and tasks are distributed across multiple machines. So you can see task is the process and data is the data. they are distributed. There is obviously a communication overhead, requires managing communication and data consistency across the network. This system is extremely fault tolerant, because in eventuality that this machine would go down, it would be automatically that this data would be shifted to this machine, or this machine may already have a copy of that data which it is not currently using, of this data, and all the process P3 would migrate to this machine. So, this is extremely resilient and fault tolerant, because you can actually sacrifice one machine without doing too much. Certain amount of fault tolerance is also there in parallel computing, where one core would fail and whatever was running there would migrate to a different machine. But here we have multiple machines. In GPU programming or in parallel computing, it was a single machine, and there were multiple cores which were running the same kind of code. Here you would have multiple machines. So, these are more resilient, and examples include cloud, grid and all that. So, often designed to handle failures of individual nodes and scale by adding more nodes. So, if the load goes up, you could add more nodes. You could add an M4 and make it do with some more data, and plus there would sometimes be a need to share data. For example, all of them would produce output which would then have to be merged or integrated. So, in that case we would have some kind of a central storage across these systems, where everything would get integrated and put together. So, this is the architecture which we would want to use for distributed computing. Multiple machines, each machine independent and autonomous, each machine having its own data and doing work, and in case of failure either the task will migrate to a new machine or one of the existing machines, and also the data would migrate. So, this in essence are the three paradigms. You should be clear in your minds what is parallel computing, what is concurrent programming, and what is distributed computing. So, this is what we wanted to convey to you.